Okay, it's time to get started. Welcome everyone, I'm glad I managed to fill the room. I will be talking about serviceable runtimes, specifically J9 and OMR related, but we'll see if we can get past that. First, a little bit about myself. My name is Bjørn Vårdal. I work for IBM. I'm a runtimes developer. I work on the J9 VM team. I'm on Twitter, so Twitter handles there. I mostly talk about runtime stuff or related, so don't worry about getting all kinds of spam. Things I've worked on, I came in a bit on the tail end of MethodHandles, did some enhancements in there, a little bit of the Lambdas work. I implemented VarHandles in Java 9 for the IBM SDK, and I'm also working actively on Project Valhalla. So back to serviceability. I think this is true. Most things die young, especially if you don't service them. True for cars, true for humans, true for runtimes. So you can think that it would be important to get a runtime that is really performant, and because it's so fast that of course everybody would want this, but I think reality is that if you can't service it, if it's not reliable, and by reliable it means it won't crash, and if it does crash, well, at least you can be relied upon to provide a fix, they're not going to pick it up. Before I go any further, don't trust anything I say. That's basically it. So the tool I want to talk about is a direct dump reader. It's, we call it DDR, of course. It's an advanced core reader, or core dump analysis for J9. Our service team uses that. Our developers use it. It's a tool that aids everything we do, so that it just knows a lot about the runtime. DDR Interactive is the front end, so I will be talking about a few different parts, and I hope I'm able to introduce them properly to you as we get to them. So, starting with DDR Interactive, just to take a look at the front end first. Hopefully you can read that. There's a command line just to get it started. If you run the jar file, which ships with J9, so J9 DDR jar is in there. Provide the core file, and it starts up and immediately says, hey, notice that you have a J9 Java VM in here. I found it, and anything that starts with the exclamation mark, as you can see in the green there, is a command in DDR Interactive. So it suggests that, hey, if you want a starting point, J9 Java VM with this address, which is where I found it, is a good starting point. It also suggests in red there, J9 help, which is where we're going to start, which will give me a lot of commands that I can use. So running J9 help, I've modified the output a little bit here, but it suggests, hey, you can run the threads command, and we'll give you a list of all the VM threads. You can run the stack command, and I will tell you the stack of that thread. You can run the stack slots command, and I will give you the stack trace and a lot of extra details about the actual state of that stack. Did we have anything else? OK, so I will be talking about the ones above a little bit. The ones further down here, class for name is another one you can run, and you get we get the internal class structure for a given class name, and some more here. Dump the class bytes for an internal representation of a class file. Find any pattern or what is at this address. So those are some of the things that the tool can do. So we are going to run the threads command. Nice dump of threads that are running, conveniently names them for me, so I know, for example, which is the main thread. And on the other side there, you can see that it, again, suggests, hey, notice that this is a thread. A good way to explore a thread is to run the stacks command. or stack command. So we're going to run the stack command, and we get this, and you can see it gives us a little stack trace. Not too much information in that, but at least we have the stack trace. You can see from the bottom that we have this class X with a main method calling M, calling print, and you can see what arguments we should expect to those methods. But if we do run the stack slots command, which is the one that has more details, so run it on the same address, get some initial output here, but starting with the yellow ones, you can see those are the ones that are actual stack frames. So I have a stack frame here, which is some internal one first, and here I actually have a bytecode frame, and you can see in red the actual method that represents. This is the print method, and in green you can see I can actually explore the arguments on the stack. And they keep coming, the different bytecode frames and some JNI frames at the bottom. So this allows me to explore any Java stack in my core file in a way that no other tool would allow me to do. So I'll show one more thing that it can do. If we do explore that argument, if you see in green, there's the argument to the print method, and I expect that argument to be a string. And the internal representation of any object in our VM is a J9 object. So, and any internal structure, the name of it, I can use as a command. So I can call bang J9 object on that address, and it gives me a nice output saying, yeah, here's your object, this is what it looks like, and yes, here's my string. As I mentioned, other tools couldn't really give me, especially, for example, the stack slots output. If we do a comparison between GDB and DDR, first a conceptual comparison, where DDB requires that I have intimate knowledge about the internal VM structures, DDR already has that intimate knowledge, so it can help me explore it. GDB would require some debug symbols to get things right, or at least to make it easy for me to explore things. DDR doesn't require debug symbols at debug time. And where GDB would require is quite fragile when it comes to matching what I'm exploring to what actually was there in the application that crashed, or in that core file. DDR is cross JVM or cross version. It supports cross version. And where GDB would be platform specific, DDR is completely platform independent. So I can take a core file from that came from Windows and explore it on Linux. Output difference, if we look at what GDB would give me if I tried to explore the same stack slots. So if I basically give it this address of the stack, this is all I get, right? I have to explore that myself, try to figure out what points where and what means what, and compare it to DDR output, which neatly gives me all the information with the right labels to tell me what it actually is. So just a couple of things that people have said in our team about the tool. First thing is, it's a tool for the service team. It's a tool they use the most and that saves them the most time. Obviously, from the previous slide, you can see that it's a lot easier to explore the internals with it. The other thing is, what we can also do is we can write plugins that can, or extensions that where we can add in knowledge about common symptoms that we have seen, and then we can just run that. When we get a core file, we can say, oh, let's check if any of the common things are a problem here, and we can easily find out quickly if we're actually dealing with a problem we've seen before. OK, staying there. Why does it matter to anyone here what we do internally with our debugging? Well, OpenJ9. We're open sourcing the J9 JVM, DDR coming along for the ride. You can explore more about OpenJ9 on openj9.org. On the topic of open source, Eclipse OMR is also involved in this, and I will show more like which components belong where later. But Eclipse OMR gives you the runtimes components you need to build a good runtime. So some links for that there. And now that I've spent a lot of time talking about different things, I will actually give you some sort of agenda. My real goal here is what I want to do is I want to put DDR in a new runtime. It's in J9, sure, but can I put DDR into a new runtime? To do that, we need something that will generate the DDR resources for me, so I will explore that. But before we get to that, I will show you a little bit more how DDR works in J9 and how it is implemented. So we already looked kind of by example at what DDR can do. But to structure a bit more, it can print a structure at an address, as I mentioned, for example, J9 object or J9 method at a given address. There are other printing commands which are more J9 specific and have to be programmed as the extensions that I mentioned. So stack slots is an example of that. There are other utility functions like finding a class, finding a pattern, finding the type of something stored at an address. So those are the utility functions. And then we also have some data analysis extensions like gccheck, which is able to analyze the heap and find out, is there a problem? Did something go wrong here? Are there any pointers that are pointing to the wrong thing? Also some deadlock detection, where it will look at the monitors and see if there's a deadlock. For example, gccheck output, where it will scan everything. This is successful output, so nothing to see really. So how does it work? So you have your runtime. We have DDR Interactive. DDR Interactive was from the J9 DDR jar that I showed earlier, and then your runtime, in our case, the J9 JVM. We put structure layout information inside the runtime, so at runtime. So in the memory, when it's running, we put this DDR blob, which contains information about the structure of everything and other information as well, into memory. That information comes from a DDR data generator, which I will also talk more about later. The DDR generator also generates code to read those structures, which is what we put inside DDR Interactive. And then what we also do is we put some detectable pattern, so a structure with a detectable pattern in it, inside the runtime, and then we point that to the blob, so we can always find this if we get a core dump from it. So in the core dump, because it was in the memory at runtime, we still have the DDR blob, we still have the detectable RAS structure. So separating things out a bit to give you a better overview, the DDR generator is currently in the source project Eclipse OMR. So you can get that there. You can already run this on your software. OpenJ9 is coming soon. The J9 JVM and the DDR Interactive tool are both in there. The RAS structure that I mentioned, let's take a closer look at that one. So as I mentioned, you have runtime memory. There's a VM structure. So there's always some kind of core structure at the core of your runtime. In our case, the Java VM structure. The RAS structure then points back to that. Simple, normal structures. It just points back to that. But also at the top, you can see it has this eye catcher, in this case, J9 VM RAS, which is what DDR Interactive will look for to find this. It also has some confirmation bit patterns after it. And then it points, as I mentioned before, the RAS structure also points to the DDR blob. So now we have everything we need in DDR Interactive to explore the rest of the memory. Let's take a closer look at the DDR blob and where it came from. So switching to OMR, there's a DDR gen in the OMR project. It can read, so you compile with debug symbols. So you need your debug symbols at this point. You don't need it later. But you compile with debug symbols, and then DDR gen is able to read the structures out of the dwarf structures. So it pulls in the libdwarf to do that for you. And then it also scans the source for build flags and macros and adds that into the information that it outputs as well. So there's a script, get macros, in OMR as well that helps you do that. You give that input to DDR gen, and it will output blob.dat. And that's your DDR blob, which you can then read into memory at runtime. It also outputs superset, which is another thing that we need to explore. So superset is what we use to generate the classes for DDR Interactive to read the blob information. So we generate structure classes that map back to the structures in the source. And then we also generate pointer classes, which basically then will be the pointers to those structures in the source. So we generate the Java files, and we drop that into DDR Interactive to allow it to load these classes and use them to point to the structures. So those are all the classes that it would expect to find. So then at DDR Interactive Startup, there's a DDR class loader in it that will load these structure and pointer classes. So it pulls in the generated Java classes as a template, and then it takes the blob data and populates the field offsets from there. So just summary of what we've done so far. We looked at some of the DDR capabilities, looked at the RAS structure and how that points to the core and to the blob. Looked at OMR DDR gen to see where we get the data from, and then DDR Interactive, how it uses the blob and the superset to get you what you need at runtime to explore all the memory. So DDR in a new runtime. That's where I wanted to get to. Can we do it? It was a very real question for me just a month ago. So the one I decided to go with is something related to OMR, where we try to use, well, base 9 is this new runtime we have for playing with OMR, like the JIT builder and other components. So it's very small. It has 10 opcodes, very easy to deal with. So I want to use it for demonstrating DDR functionality. There's a link to my fork of the project there, so you can see the work I actually did to get this working. And I just want to mention that what I got out of this was a very quick prototype. It was about an hour of hacking, and most of it was copied from J9 JVM, which when you want to do the same thing will also be available. So back to this RAS structure graphic that we had before. We have the RAS structure in the middle, the DDR blob, and the Java VM structure in the J9 case. So all I really have to do is just copy the same structures over and point to the execution context, which is the core of base 9 instead. So I kept everything else the same, same eye catcher, just to play nicely with DDR Interactive. And then, of course, the DDR blob I got from running DDR gen on base 9. In terms of code changes, not very much. I threw in this structure here. That's the RAS structure I expected. So it has the eye catcher, as you see highlighted at the top, and a pointer to the VM or to the execution context highlighted further down there. I added a couple of methods, one to initialize this structure, just throw in all the information that I have, and another one to read that DDR blob file and just get that into memory. Nothing magic about that, just allocate enough bytes, same size as the file, read the file, write in, done. And then in the execution context, which is the core structure of base 9, I added a field for it and added a call to the constructor, and that was all I needed to do to DDR enable my base 9 runtime. So now it looks like this. I have a pointer to the blob, a pointer to the execution context, DDR enabled. DDR Interactive, a little bit more complicated. It's definitely a bigger project, a lot more to it than the DDR gen portion of it. So what did I have to do to get DDR Interactive to work with base 9? I disabled all the J9 specific functionality. That includes, for example, stack slots, because the way the stack is set up in Java, in the J9 Java VM, is of course not the way it's set up in base 9. So basically anything that depended on certain structures was out. I told it to look for the B9 RAS structure instead of a J9 RAS structure. Nothing big there. And I have to add a bunch of build flags manually. So I forced it to always go to 64-bit and a few things like that. But in general, not many code changes at all. It was mostly just disabling the dynamic portions of DDR Interactive. But again, as I said before, it was quick hacking. It was about 1 hour. So the result, it works, but not very advanced functionality. But let's take a look at it. I'm going to switch to live for that. Let's see where I am here. So the B9 that I have here is DDR enabled. So I'm going to go ahead and run B9 with some program. And I've injected a hang at the end here just to give me a chance to get a core file. So here I have my core file, and that's my input to DDR Interactive. So if I now run, let's see, DDR jar, and run DDR Interactive with that core, what did I do? And immediately it finds, let's see if I can, where am I? OK. At the bottom, you can see it finds the execution context immediately, because, again, it just looked for the RAS structure and found that. So it knows where the core element is. I also outputted the RAS structure above there, so you can see it finds the expected bit patterns and things like that. So the suggested command is to run execution context. I will do that, and here you can see it has the structure. It pulled that structure out of the debug symbols, stored it into the blob file, which I read into memory. So now I am able to print that structure again from any core file that I get handed from B9. Just want to do one more. I got this. It said it found the RAS structure here. So I'm going to see if it's willing to give me that. So I know the name of my structure is B9 RAS. I gave it the pointer where it said it would be. And as you can see, maybe you can't tell from the eye catcher, but from the bit patterns, they are exactly what we expected. So then I can explore all of my memory from here with suggested commands for what I should find where. Let's see. It's not giving me my presentation back. There we go. So what's next for DDR? I really want to make DDR plug and play. So basically, not have to do the changes I have to make to get DDR Interactive to just work. So if you have a DDR-enabled blob file, I want it to run. Or DDR-enabled core file is what I should say. It would be nice to simplify the DDR generation process. And of course, we need to release DDR Interactive and the generator. So generator is out. Get DDR Interactive out as well. So quick conclusion here. We looked at DDR in J9, the capabilities, how it's implemented. DDR Gen is what gives you the resources, the data, the blob file, the superset to be able to DDR enable your runtime. And then we were able to make it work in base 9, where we can now explore the internal structures. And that was my presentation.